Hi there everyone, in this video we're going to be talking about the second part of sampling, and that is in the syllabus. It specifically mentions that we need to know about graphical displays of simulated data to investigate the variability of random samples. And I think I talked about this a little bit in the last video, that because we're taking samples from the population, every sample we take is going to be unique, especially if the population size is large. So if we've got 1,000 people and we're taking samples of size 20, every sample that we take is likely to be different. You ask 20 different people, you're going to get a different response. Even if, say, in different samples you might have some of the same people. So the variability among samples is what we're looking at here, and it also specifically asks us to be looking at uniform, normal and Bernoulli. So I'm going to be going through how you use your calculator to do a random sample from these different kinds of distributions. The underlying theory behind this stuff is called the central limit theorem. Now this isn't part of the course, but I wanted to do an introduction because this is the underpinnings of everything in this unit that I'm going to talk about from here on. We're going to get into the next bit is going to be about proportions, but I'm going to talk about the central limit theorem in terms of the context of a really basic example here where we've got a bag containing 100 digits, 10 each of 0 to 9. Let's say they're on plastic cards. And so what kind of distribution do we have? We could draw that and see what it looks like. So here we have the distribution for that situation, okay? So we've got the numbers 0 to 9, and the probability of getting any one of those numbers when we first choose one out is 0.1. So that's the probability distribution there. Suppose that we drew 10 digits now at random and started to add them up. What does the distribution like for a sum of 10 digits look like now? That's a little bit different. So what's the smallest possible number? Well, I guess we could get 10 zeros. That'd be unlikely, but we could. So we could get 0 for the total. What's the biggest number we could get? Well, I guess we could get all 10 nines, in which case we could get 90, but the probability of that is extremely small. And hopefully you agree with that. The chance of getting all the nines, well, you'd have 10 out of 90 to start with, then 9 out of 89 times 8 out of 88 times 7 out of 8, etc., etc. It's really phenomenally small likelihood. Every value between those would be possible. The most likely value, I'm guessing, would be around about 45 for the total sum. Is it discrete or continuous? Well, in this case here it would be discrete because you couldn't get 48.6 for the sum, so it would be discrete. Here's what it looks like. In fact, when I do that and we look at the probability distribution, here's the probabilities down the side. So 45 is about the most likely sum, but you can see even the most likely sum only has about just over 8% chance of happening. You can see once we get round to totals of 29 or 61, the chances are very, very, very small. And we've talked about 0 and 90 at either ends would just be phenomenally small. So this is the distribution. You recognize that as a bell-shaped curve, and that's exactly what the central limit theorem is all about. When we take random samples from a population, and it doesn't matter what kind of population you sample from, we end up with this normal distribution curve. Here is a great little demo of what I'm talking about. Here I've got a normal distribution to start with. It's got a mean of 16, standard deviation of 5. And what I'm going to do is take a sample of size 5 from that population. Then what this does is it calculates the mean of those 5. So I'm going to do that again. Here's a different sample of size 5. Now you would expect from this population that it's more likely to get values here within one standard deviation of the mean. We've got some low ones here, so our sample mean is lower. So we're going to do that again. That's more likely. Here's a real random one out the front, but I guess the average of those 5 values is here. Now if I do this over and over again, look what happens to the sample means. I think you'll get a sense from this that even if we got extreme values in our survey, eventually if we average them all out, we're going to get a value towards the middle. So if I do that 5 times and another 5 times, and I'll keep doing that, let's do that 10,000 times. So I did that 10,000 times. I took a sample of 5, I averaged those 5 numbers, and I put that average down here. So eventually we get this frequency distribution you can see, which is normally distributed. And other thing you'll notice is that the standard deviation of this one here is smaller than this one up here. Let's change this now and do the same thing. So we're going to take random sample of 5 things, 5 objects from this population here. This is the parent population. And that the blue one here represents the mean when we do that. So these are just random 5 values. And there we go for the mean. Now if I did that many times, 100,000 times, you get this normal distribution again. Most of the samples means are around about the middle. This is the central limit theorem in action. If I change, so instead of taking 10, let's do samples of size 20. So now what it's doing is it's taking 20 values from the population and then averaging each one of those out to give me one blue value, which is the mean. If we do that 10,000 times or 100,000 times, we can see we get this normal distribution. So this is the central limit theorem in action. And this also works no matter what kind of distribution. If you start off with that, you end up with a normal distribution. So I could create my own distribution here. So something really interesting like this. And let's choose a sample of size 20 from that population. So we've got some from the top, some from the middle, some from the bottom, average them out, and we get the blue one there. So we do that a number of times. Again, we get that normal distribution. This is the central limit theorem coming into play. So let's go to our calculator now and work out how we can do these samples on the calculator and have a look at them. So this is saying let's generate 2 samples of 15 items from a uniform distribution on the interval 30 to 50, placing each sample in a different column of a spreadsheet. Okay, I'm going to draw the graph and then compare them. So here's the steps that you would go through to do this. We want to be in decimal mode. We're going to use this function here called randlist. Randlist will give us a list of random numbers of a certain length here. Okay, so in this case there's going to be 15 of them. So randlist 15 will give you a list of random numbers between 0 and 1. But what we've done is we've times it by 20 and added 30 to make sure that we've got numbers between 30 and 50. Okay, so imagine a number between 0 and 1 we've times by 20 and then we've added on 30 to that number there. Okay, so that gives you this big long list of numbers. You can only see the first couple, but if you press the right arrow you'll be able to see all of them. And then we've put that into list 1. So that's just the little arrow. If you go to the Math 1 menu, that little implies arrow, and then I've typed list 1. Done the same thing again and put those into list 2. And we've now got 2 lists of numbers that we can then access from the stats menu. So if we go to the stats menu now, if you go set graph and setting, we want to make a histogram, frequency of 1. You can see those lists are in there, and we can then see in this case here we want to start to do the graph. We want H start 30, so we're going to start from 30 and a step of 3. You could change the step if you wanted to 2. So we tap the top half of the graph and repeat this using H start and step 0.5 to get a different kind of graph there. So here's the graphs that you might end up with, something that looks like this or something that looks like this if you have the step size much smaller than the other one that you had before. Same thing from the normal distribution. Mean 25, standard deviation of 6. We're going to sample of 20 items. So rand norm is the function that you want. Let me show you where to find that. Okay, so now I'm on my class pad and I want to do the normal, rand norm. So if I go down, just click the down arrow here and go to the catalog, scroll across till I get R, you can see I've got rand binomial, so this would do a sample from the binomial distribution, random list and random normal. So I'm going to choose random normal, input that one. Now I want 3 things in there. The 3 things that I want are the standard deviation first, then the mean, then the sample size. That's what you have to remember. So here we want standard deviation 6, the mean is 25, and we want 20 samples there. Okay, so I do that and I get, there's my sample of size 20. If I can scroll across I can see the rest of them. Now I want to put those into a list, so I could do that. I could do it obviously at this step here, or I could then just go back to my Math 1 and say I want to put the answer into list 1. So you can go to your keyboard and type in list 1 and then press execute. That puts the list into list 1. We can then go to the menu, go across to statistics, and our numbers are written in there. Okay, so they don't look like decimal numbers, but there they all are there in list 1, my 20 random numbers. Now I can draw a graph. So the type of graph I'm going to want to draw is a histogram. Frequency of 1 is fine, so I could set that and then select here. Start at 14, that's fine. The step we could have, let's say 3, okay, and there that will draw a histogram of the samples that we drew. You can always go back and change that. So start 14 and have a histogram of a step of 1. There we go. So that shows our samples for that particular one there. If we now wanted to get a random sample from the binomial distribution, let's say with n is 24 and p equals 1/6. Same thing, get across to the catalogue, go for R as the values that you want, and rand_bin is what you want, random binomial. Now the parameters that you need are the mean, so the n, number of trials, p, the probability of success. Okay, so if you just hit that 1, it'll only give you one of them. So basically that's saying like we had 24 trials, we rolled a dice, chance of getting a 6, what's the 4 is the output that we got for that one random variable. If we do it with the 20 on the end there, now we get 20 of those. Alright, so we rolled a dice 24 times and we want to know how many 6s did we get. So the first time we did that we got none, second time 3, etc. Okay, so we want to put that answer into a list. So again, answer into, go to our keyboard and you can type list 1 or list 2. Press execute and then those are available. If you go to the menu, go to statistics, there's all the numbers that are in there and you can now draw a graph. So the same thing we did before, change scatter to histogram, set that and then draw the graph. Start it at 0 and let's make the steps 1, that makes it look a bit nicer. And there's your graph of the results showing, in this case, the binomial distribution. You've done a sample from the binomial.